Greetings, AP Chem. Today we're going to be talking about photoelectron spectroscopy, which we talked about in our previous lecture. It's also known as PES. And so photoelectron spectroscopy is a technique that uses electromagnetic radiation to take a look at the inside of an atom. And that's what we're going to kind of get into today. So the general idea of how photoelectron spectroscopy works is that it takes advantage of something that we call the photoelectric effect. It's actually something that's discovered by Albert Einstein. He gets, I believe, his Nobel Prize for it. And so the photoelectric effect is an occurrence where electrons are emitted from substances, which means that they leave the substances when you hit them with a high enough energy light. So if you have an atom and you hit it with a high enough type of electromagnetic radiation, you can actually kick electrons off of that particular sample. And so that is how the photoelectric effect works. And so what ends up happening is that if you can observe the electrons that leave your sample, you can actually learn more things about the atomic structure of it. And that is generally how that works for PES. Okay, so here is a very crude drawing of what ends up happening when you are running a photoelectron spectrometer. So what ends up happening is that you have this photon source here, and the photon source is usually some sort of either ultraviolet light or an X-ray that they have, and you tune it to a specific frequency to accomplish kind of what you want. And so then you have your sample here, and then the electrons kick off and then are scooped up by this energy analyzer, and then you end up getting a graph from it. What ends up happening, and you guys know this at this point, is that ultraviolet radiation is lower in energy than an X-ray. We talked about that with our electromagnetic spectrum. So what happens is this photon source here can get cranked up. So we can turn it kind of higher and higher energy. They start off with the lowest frequency and then crank it up and then increase the energy. And what happens is, from what you know now at this point, your electrons sit in kind of like layers around your nucleus. And so what happens is they generally start off with ultraviolet electromagnetic radiation, and then they hit the electrons. And what ends up happening is that usually the outside electrons are relatively easy to kind of kick off of the atom, and so you don't have to apply a ton of energy to make that happen. So ultraviolet light is where they start because it's the lowest in energy, and then once they remove kind of that first shell of electrons, they try to use the ultraviolet light at a higher frequency. What ends up happening, we'll get into this in way further detail, the deeper you get into the shells and the closer you get to the nucleus, the harder the electrons are to remove. So they'll start off with ultraviolet radiation, and then they'll crank up the frequency and then try it with ultraviolet again at a different frequency. And then if that works, they'll take off the next layer of electrons. And they keep on going with that until the ultraviolet light stops working. Then they crank it up into the X-ray range, and when that happens, then we start taking off electrons that are closer to the nucleus. The very first layer of electrons on the outside, if you recall, is called a valence electron, and that's the outside electron. In the inside of the electrons, you end up having what are called core electrons. Core electrons are like the little core that's nestled in, and then the valence is outside of it. And generally, those core electrons are held onto tighter, and they are harder to remove, so you need an X-ray to make that happen. Okay, so what ends up happening then is that they measure out the energy that comes from the photon. So this h nu is like the calculation that we talked about in our previous lesson. So if they know Planck's constant and they know the frequency of the light coming out, they know how much energy they put into that sample. And what they do is they actually measure with the kind of receptor for the electrons, they measure how much energy, kinetic energy, that particular electron has when it leaves the sample. The difference between the kinetic energy and the energy total that was put in is something called the binding energy. Okay, the binding energy is what they use to put on the graph there. And so again, we're going to get a graph that shows the different binding energies that result from cranking up that particular laser or beam as you go along. Okay, what you end up getting is they call it a PES spectra or a photoelectron spectra, PES diagram, whatever you want to call it, that looks something like this. So in general, what happens is that the y-axis is always the number of electrons that you have. The x-axis is the energy, that binding energy that we talked about that it takes to remove that electron. And the binding energy is measured in something called electron volts or megajoules. And these are not things you need to worry about. You just need to pay attention to the numbers on the axis and the height of the peaks, because the peak heights are going to be important. Now, this is the PES diagram for hydrogen. Hydrogen is an element with, as you know, only one electron. And so this is what the diagram looks for hydrogen. So when they did that and they cranked up the laser and they got the energy analyzer out, they got this diagram for hydrogen. Now I'm going to show you a picture of lithium, and then we will kind of talk a little bit more about that. So lithium, if you get out your periodic table and you take a look at it, lithium has an atomic number of 3, which means it has 3 electrons total. And so this is actually what you get for the PES diagram for lithium. And if you look, there is one peak that's a higher energy value, and then there's a peak that's lower in energy, and it also has only like half the height as the other one. I'm pointing, but like, what is that accomplishing? So what ends up happening is, like I said, the inner electrons, not the ones on the outside, the valence, but what we call the core electrons, those are harder to remove. So when you look at a graph, what you want to do is you want to look at the energy, okay? Once you look at the energy value, find the highest energy value, because the way I show my PES, there are different graphs that you can see, and we'll kind of take a look at those in just a little bit. So what ends up happening is that always find the highest value. The highest value on your graph is going to end up being the electrons that are closest to your nucleus, okay? So since this has a value of, I don't know, in the neighborhood of 8, and this has a value of less than 1, I know that this peak here is going to be my electrons closest to my nucleus because it's got the higher energy value. This is going to be my lower energy value down here, the one that's below 1. The other thing that's important is if you look at the peak height, the height of the peak in the lower energy value is approximately half the height of the peak for the higher energy value. And what this tells me is that the number of electrons that are present at the higher energy are twice as many as the electrons at the lower energy. So relative to each other, this first peak, where I'm taking these electrons off very close to the nucleus, has twice as many as the other one. And so if we think about that in terms of lithium, it only has 3 electrons, so it's going to be 2 and then 1. And if we talk about, we're getting into electron configuration, this is where electron configurations actually come from. So it's just kind of interesting. We are going to end up talking about something called effective nuclear charge later on. That's going to talk to us about comparing one atom's PES diagram to another, but right now we're just going to be taking a look at individual ones. So like I said, if you kind of harken back to your electron configuration in your regular chemistry, this tall peak here, that's the 1s peak. And if you remember, S shell can hold 2 electrons. This would be our 2s peak. Okay? This is example number 1 that I'd like you to try. So I want you to think about this, pause the video, see if you can identify what element this thing is. Okay, so pause it, get your periodic table out, and give it a try. All right, so coming back to this, this particular element, if we look at the peaks here, we have the highest peak at like between 100 and 1,000, and you'll notice that the scale on here changes, and that's not super important. All you got to do, find the highest peak, okay? So here's our highest peak. This is the element's electrons that are closest to the nucleus. So if we start out, we've got our first peak, which you know is the 1s shell. So that's 1s and it's full. 2s has the same amount in it. Notice that their peak heights are the same. So it's 1s2, 2s2, big peak here is 2p6, 3s2, 3p6, and then this peak here, this furthest out peak, that is the valence electron because it takes the least amount of energy to take it off. And so that valence electron there has 1, and it's in the 4th kind of level, 1, 2, 3, 4. So this is our 4s1, which means that this element is potassium. Okay, hopefully you got that. Okay. Next one. This looks a little bit different, but it's exactly the same thing. Okay, so take a second, pause the video, see if you can figure out what the electron configuration is here. This one's kind of nice because it tells you how many electrons are actually in the peaks. Okay, so pause it, take a guess. All right, if we check for our answer, find the highest energy value. So again, the energy diagram is the same, but if you look, it's actually backwards on this one. So energy is still on the x-axis, but in this case, it's going from low to high. So like I said, sometimes the PES diagrams can be a little bit different. So if we find our highest energy value, that is 39.6, and there are 2 electrons in there. So that's the 1s2 electrons. You find the next highest one, that's 2s2, and then the next highest one is 2p3. And if you find 2p3 on your particular thing, you should get nitrogen. Okay, so again, 1s, 2s, and 2p. 2p3 is nitrogen. So you may be asked to read a PES diagram. I've seen it quite a bit on the most recent exams. They could ask you a question about which peak represents a valence electron, which peak represents a core electron. It kind of just depends on what the question is asking. But just be aware that you need to be able to read these, okay? We're going to be getting into electron configuration and stuff like that in just a little bit. And so hopefully you have good luck with this. I have some examples that we will be going through, but for right now, you can just get these PES diagrams, and if you've got them figured out, you should be good to go. Good luck.